Okay. Hi, everyone. It's good to see you all and to have Andrzej Grzesik to speak at our seminar. He'll talk on generalized Turán problem for cycles. As usual, if you have questions during the talk, Andrzej, are you okay being disturbed by?
Yes, yes, please feel
Okay.
free to do it.
Yeah. So, and also at the end of the talk, we'll have some time for question and answers. And then if you don't want to be recorded while you're asking a question, there will also be some time where there's some informal discussion. So yeah, can start, Andrzej. Thank you.
Thank you very much. Thanks, Liliana, for invitation to the seminar. I'm happy to be here and give you some piece of my research. I will be talking about generalized Turán problem for cycles, and this is based on two papers, one with my PhD student Bartłomiej Kielak and one with my master student Mateusz Górski. Since this is an extremal combinatorics webinar, probably everybody knows the Turán problem and what are Turán numbers, but let me do a short introduction to the topic. So by this X and F, I denote the maximum number of edges in a graph on n vertices, which does not contain a specific subgraph F. And I'm talking about the non-induced containment of a subgraph, of course. So what we know about those numbers since already 40s, we know that if the graph is not bipartite, then the extremal number of the maximum number of edges is of a quadratic order. And moreover, Earthstone theorem gives us exactly what's the constant here, right? So we know the exact answer in asymptotic way. But if the graph is bipartite, then this number is just zero. So we don't get such a bound. We have some lower order. And we know, and not much is known when F is bipartite, right? We only know that it will be of a lower order than quadratic. I mean, the graph will be sparse, external graph, but usually we don't know even the correct order of magnitude. And for the cycles, which is the topic of my talk, we know the correct order only in the case where when the cycle is of length 4, 6, or 10. Right? In other cycles, even cycles, we know only the bounds. We don't know what's the correct order of magnitude. Right? So we emphasize in the dense setting, we know basically almost everything, right? We know the correct order of magnitude, we know the correct constant, while in the sparse setting, even order of magnitude can be a hard problem. And in the generalized Turán problem, we are not maximizing edges, but maximizing the number of copies of a particular graph page. For easier remembering which graph is which, I will be always denoting F, the forbidden graph, and it will be always the last one in the notation here. Okay, so as before, I'm forbidding some graph F as a subgraph, and I want to maximize the number of copies of a specific graph page. So historically speaking, this was known since Zykov and independently Erdős for cliques. So if I forbid one clique and try to maximize the other one, then still the maximum is, as you can imagine, just achieved in the Turán graph. So this can be easily proved. And historically speaking, then what happened is the Erdős Pentagon Conjecture. This is 84, which the conjecture was giving the bound for maximum number of pentagons if we forbid triangles. And this was stated in the 80s, and there were just one important result by Jerry in 89, which basically solved the problem up to like 3% bound. Right? There was a multiplicative error term here. And since then, almost nothing was happening with those generalized Turán problems till two breakthroughs, let's say. First one was the solution of this Erdős Pentagon conjecture, and I will tell a bit more about the solution. But the more important fact is that it was done using flag algebras by Rasborov. This is new method of finding some bounds for graph densities, and this can be used in many other settings, so it's very helpful in generalized Turán problem. And a few years later, Alon and Schickelmann, they wrote a paper which was investigating those numbers for classical types of graphs, I mean complete graphs, complete bipartite graphs, trees, and dependencies between them. So basically, this paper started some systematic search for those generalized Turán numbers. And since 2016 of publishing this paper, there are lots of results on the topic. Let me say, for example, that the Alon Schickelmann paper has more than 120 citations, which shows how the topic developed in recent years. So in order to say what's known, let me start with this division as it was for the Turán problem. I mean, what's the sparse setting and what's the dense setting. Here, if we consider a blow up of a graph that we want to maximize, a blow up of a graph, if I have a graph and I want to consider its blow up, I just take a blob of vertices for every vertex in my graph and connect by complete bipartite graph whenever there is an edge in the original graph. Yes, so if I consider such a blow up, then of course it has a n to the power of a number of vertices in h copies of a graph h, and if it does not contain my forbidden subgraph f, then it gives me a good order of magnitude, and it cannot be better, of course. Yeah, so this is quite easy to observe that if f is not a subgraph of a blow up of h, then this extremal number is of this order. Right? This is the equivalence of for the Turán problem for a graph which is not bipartite. While if a graph is a subgraph of a blow-up of the graph that I want to maximize, then we know that the order of magnitude is smaller. Right? There is some epsilon dependent on the graph that we want to maximize and the graph that we forbid. And the order of magnitude of this number is definitely smaller than n to the power of number of vertices in graph H. This is easy to observe by using some regularity or graph counting, things like that. So this is easy to observe, right? So this is the division between the sparse case and the dense case. Of course, if you look at the standard Turán problem, there we were maximizing number of edges. And of course, bipartite graph is the graph that appears in the blow up of an edge, right? So this is exactly the same speed. Yeah, if my forbidden subgraph is if the forbidden graph is a subgraph of a blow up that I will maximize, then we have this sparse setting. And if it's not, then we are in the dense setting. Right, and as for the Turán, standard Turán problem, in the dense setting, we know the order of magnitude, and our problem is to find the constant, right, to get the asymptotic result. And while in the sparse setting, even finding the correct order of magnitude might be hard, right? So there, any order of magnitude would be interesting. Okay, so there are lots of results in this direction, as I mentioned, including paths and many other specific graphs. I will not mention those results. There are lots of them. Here on the talk, I will just focus on both graphs. I mean, the graph that we want to maximize and the graph that we forbid are cycles. Yeah, so I forbid some specific cycle of a specific length, and I want to maximize some other cycle. Okay, so what's the split between the dense case and the sparse case? So one cycle is a subgraph of a blow-up of another cycle. Of course, when the cycle we want to forbid is even, right? If I have an even cycle, it appears in a blow-up of an edge, so it appears in a blow-up of any other cycle, right? Or if they are both odd, then the cycle that we want to maximize, which is the smaller one, here we draw it. So if you take a blow up of a triangle, then of course there appeared any cycle of any odd cycle of a longer length, right? Because you can walk between the two parts and then complete the cycle around. Yeah, so the split between the dense case and the sparse case is the following, as it's written here.
Andrzej,
yeah, yeah.
Can I ask, the blow up of the 3 cycle will give you all the 3 chromatic graphs. So wouldn't every odd cycle be a blow up of a C3?
Yes, but if you consider a blow up of a C5,
okay, you're saying for every
triangle there. Yeah, okay. You can find for only right. Cycles which are longer. You will not find cycles which is shorter.
That's right. Okay, thank you.
Yeah, you're welcome. Please interrupt me whenever you have some question. Okay, so the order of magnitude for every K and L, and K at least 4, which means except maximizing triangles. This was determined by Boliner and Shapira recently, and independently by Gerner, Jerry, Natuku, and Wieser in the case of even K and L. So this case that we thought that is harder. And in the missing case, when we are maximizing triangles, we have bounds, but they depend on the Turán number of even cycles, right? So as I said, these numbers are known for some specific cycle length, and for those we get the bounds here. And whenever we don't know the exact bounds for the standard Turán problem for even cycles, we don't know the bounds here. Yeah, so let's say up to the Turán problem for even cycles, we know the order of magnitude of the generalized Turán problem for cycles. Right, so here what we are still missing is solving the problem asymptotically. Okay, let me focus on the dense case and sparse case separately. So I will now be doing just the dense case, and in the second part of the talk I will do the sparse case. Okay, so in the dense case, we have 2 cases basically. Either cycle we want to maximize is even, and the cycle that we forbid is odd, or they are both odd, and there is an inequality between them. So in this first case, when K is even and L is odd, this is very easy, because if you consider a complete bipartite graph, then of course it does not contain any cycle of odd length. And moreover, at the same time, it contains quite many cycles of even length. And it occurs that this is exactly the best you can do. Well, just if you want to maximize any even cycle and forbid any odd cycle, then just take complete bipartite balanced graph and you get the maximum. So this is it. And the second case is when they are both odd and the cycle that we want to maximize is longer than the cycle we want to forbid. Right? And in this setting, the smallest case is when L is 3 and K is 5, which is maximizing pentagons in a triangle-free setting. And this is exactly the Pentagon Conjecture. So as I said, this was solved in 2012. It was solved independently by me and Hatami, Hlapki, Karl, Norin, and Rasborough. And we both use the method of flag algebras, which is computer assisted. And later, Levitsky and Fender even provided complete characterization of all external examples. And so now we know that this problem, the pentagons in the triangle-free setting are maximized in a blow-up of a pentagon. All right, so I just take a blow-up of a pentagon, except one sporadic example on 8 vertices. And this blow-up needs to be as balanced as possible. And so basically in this problem we know everything. The problem is that the method that was used here is computer assisted, and so it's hard to generalize. Right? It requires, for example, generating all graphs on the number of vertices, which corresponds to the size of the graph that we maximize. In particular, if I would like to obtain similar result for maximizing, let's say, 9 cycles, then I would need to generate all graphs on 9 vertices, and this is enormously big number already. So you cannot work on flag algebras on such a big number because it's a too big space. It's too many dimensions, and it's basically impossible for nowadays computer. Yeah, so it's nice that this problem was solved, but unfortunately the method was we're not able to generalize this method for longer cycles. So what we did with my PhD student, Bartek Kielak, we managed to solve this problem for maximizing any cycle of odd length if we forbid cycle which is just too smaller. Yeah, so I forbid any odd cycle, for example, C9, I forbid C5, and I want to maximize C7, which is just the next step after the Pentagon Conjecture. So you may ask what can be said in general. So if I not forbid K-2, but some smaller odd cycle, and we conjecture that the best is just consider a balanced blow up of a cycle of like L+2. Yeah, so if you forbid a cycle of length L, like triangle, then the best you can do is just take a blow up of a pentagon. Whenever I forbid triangles and want to maximize some other odd cycles, like C7, C9, etc., just take blow up of a pentagon. And this gives you the asymptotic solution. That's what we are conjecturing. The bound here looks quite terrible, but this is just because if you want to find some longer cycle here, you can go there and back, and there are many cases how to do it. This gives you this big number. But what's important to remember that the conjecture states that you should take a blow up of a cycle which is just slightly bigger than the cycle that we forbid. Okay, and how will we prove it? So the exact statement of the theorem that we proved is the following. So for any integer, odd integer k, and any graph without odd cycle of length less than k. So we do not forbid the cycle of length k-2, but we forbid all smaller odd cycles. And we say that the biggest number of k cycles is exactly n over k to the power k, and moreover this bound is achieved only in the balanced blow up of ck. So this is the only external graph for this problem. And you can easily see that this gives the asymptotic solution for the problem of forbidding cycles of length k-2, because there cannot be too many smaller odd cycles, right? Because in a blow up of a smaller odd cycle, we will find cycle of length k-2. Okay, and how the proof is done? So what we do, I'll try to do it. So if we start with some path, let's say we already managed to find path of length 4, and we are consecutively finding vertices which can close up at the end into the cycle of length k, the induced copy of the cycle of length k. So I look at the vertices which can prolong the chosen path, right? So I get a set of vertices. Let me say that this is a set of size n5. And these are the vertices that can be used to build a cycle of length k, like the odd cycle of length k. And when I want to be induced, because of course, any cycle of length k in a graph that does not contain any smaller odd cycles, it's induced, right? If you drew any diagonal in an odd cycle, then you create a smaller odd cycle. Okay, so this is n5. Let's be the number of vertices that can be used to prolong this path. And then if I choose any of them and prolong it further, I have a set of size n6. And what's important to notice is that those sets are disjoint. I cannot prolong inside here because at the end I want to obtain a graph, a cycle which is induced, and here it won't be induced because I have those additional edges, right? So those sets will be disjoint. And I can continue like this till I close the cycle. Okay, and if I close the cycle, what's the number of possibilities to prolong this path? This is just the product of those numbers, right? And this is nice because if I have such a product, I can easily bound it using arithmetic and geometric mean in terms of its sum, and the equality will be when they are equal. And this is exactly what we can see in the external construction, right? In the blow up of a K-cycle, you have exactly such blobs, and these are exactly the sizes of sets so you can prolong the cycle. The problem is that at the beginning, we cannot do so easily, because if I take first two vertices, say it's 1 and 2, and then if I look for the third vertex, I cannot just take a neighbor of vertex number 2, because if you look at the extremal example, it can be in the next block, which is nice for me, or it can be in the previous block, which is bad for me, because this cannot be prolonged in this second setting. This cannot be prolonged to the induced copy of the K-cycle in the extremal construction, right? So those choices are bad for me because they are not giving me anything. And if I use the number of vertices in each, like the numbers of neighbors of the vertex 2, then I cannot average as in the previous case, because I will count too many vertices which are not useful for me to create a cycle. And to avoid this, we use a following trick. So after choosing those first two vertices, we take a vertex, basically number 4. I mean, vertices which are at distance 2 from vertex number 2 and distance 3 from vertex number 1. Yeah, so this gives me a set of vertices which can be used, and this is my N4.
Sorry,
and now
do you mind going a bit slower here?
Yeah, no problem.
Yes. So how did you define this Ni? Ni was just the number of
vertices that can be used to prolong my cycle, right? So if I have a path of length 4, for example, at the beginning, and I want to prolong it so that in the end I will have a blow up of a K-cycle, I will have a K-cycle, then the 5th vertex needs to be connected with the 4th vertex and not connected with 1, 2, and 3. Yeah, so I can consider a set of vertices in my graph which are connected with the vertex number 4 and which are not connected with vertices number 1, 2, and 3. And this gives me a set of vertices of size N5.
Andrzej, sorry, can you explain the previous point? Why the second step is that if 3 lies in the same block as 1, it's a bad case? Can you explain that again?
Yeah, no problem. So if I want to choose the same way as I was choosing the path here in the third vertex, if you look at the extremal example, so the third vertex, if you define it as just connected to vertex number 2 and not connected to vertex number 1, it can be in the extremal example, extremal construction, either in the next block or in the same block as the vertex number 1. Right? And if it's in the same blob as vertex number 1, notice that now I cannot find any vertex number 4. I mean, vertices in the next blob will be connected with 1, and vertices in the next.
So I won't be induced anymore. Mm-hmm.
Yeah, so you cannot prolong it to obtain a K-cycle, induced K-cycle. So those vertices are not used. So I cannot use them in bounding here. I can use just by multiplying here because I will lose it. I will not obtain an exact bound.
Okay.
Yeah, so I need to define those vertices number 3 in a bit different way.
Okay.
Yeah, and the trick is to firstly define vertices which will be used as number 4, and then define vertices which are used as number 3, basically as joint neighbors of vertex number 4 and vertex number 3.
Okay, just to ensure induceness. Okay.
Yeah, so if I do such a trick, then it works in the extremal construction, And in general graph, I need to argue that those sets will be disjoint. Now it's a bit different argument because they are not only, I cannot just look at the neighbors of vertices, but I need to also look at the distance to vertices. But still it can be done. And this way I can achieve that those sets will be nice and I can average it using arithmetic and geometric mean and obtain a good bound. Okay, we'll continue. This is exactly what I said. Okay. Yes, and the last problem that we need to solve is the fact that vertices which are in the first block, I mean, the first vertex I can choose in n ways, right, where n is the number of vertices in a graph, and the vertices in its block are not used in constructing a cycle, right? So those are useless vertices for me. And in order to overcome this difficulty that there will be some useless vertices, I'm not counting over like a single choice of a cycle, but averaging over all rotations of a cycle. This way, and like if I average over all n over all k rotations, each block will be not counted once, and then it's everything average up to a correct number, and it's yeah. So basically, this is just counting together with arithmetic and geometry. This method was used by Kral, Norin, and Volet earlier before us to obtain some result on inducibility of cycles, and this is just adopted for this setting. Okay, so what I want to emphasize is that this is very short. This is the whole paper is like 6 pages, and gives a full generalization of the Erdős Pentagon Conjecture. It was open for 25 years. And the funny thing is that this does not work for k equals 5, because for k equals 5, this trick with getting vertices which are at distance 2 from vertex 2 and distance 1 from vertex 1, distance 3 from vertex 1, in the blow up of a 5 cycle, there are no such vertices, right? The cycle is too short to make this trick work. Yeah, but that's why this is working only since k equals 7. Yeah.
So Andrzej, isn't that because of the previous picture you drew, like on the previous page? If you go back,
I cannot because Zoom is.
I see. Yep, there was this thing, right, that you could have the one to be coming from the same blob, and that would not. If k is 4, this no longer contradicts to being induced, while k is at least is that where you use it?
Yeah, like you cannot. The cycle is too short. I mean, because this set is not only vertices which are at distance 2 from 2, but they are also distance 2 from 1 using a different path, right? I cannot define it as distance 3 from 1, as it was defined in the previous case. And here, basically, the counting will not go correctly. I mean, I cannot define it properly with this block.
Okay.
Okay, so the nice thing is, and I want to emphasize it, that if you take longer cycles, the problem appears to be far easier than for shorter cycles. Okay, so let me leave the odd setting here and move to the sparse setting, unless there are some other questions. No, so let's move to the sparse setting. In the sparse setting, in the twin case, but now we are forbidding 5 cycles and maximizing triangles. We had many improvements on the upper bound, and the correct current best bounds are the following. So we can see that we know the exact order of magnitude, because n to the power 3/2, and we have some bounds on the constant, which are already quite close. But still, we cannot solve it even asymptotically. And for longer cycles, still in bounding triangles, we know similar bounds, also depending on the extremal number on even cycles in the standard Turán problem. They were obtained by Jerry and Lee and then improved by Alan Schickelman in the paper that we already mentioned in Kiredi and Górski. Okay, the same was done by Grzesik and Shapira to extend for forbidding even cycles, not odd cycles, and we get bounds which are also depending on the Turán number of even cycles, right? So we still don't have a correct order of magnitude in most of the cases.
Andrzej, can I ask you? So my understanding is that these bounds are reduced to the Bayes Turán number of these cycles, right?
Yes,
Okay.
exactly. So in particular, if you solve the Turán problem for even cycles, then you get the correct bounds here. I mean, it shows both lower and the upper bound depending on the bounds for the Turán problem. And there is only one basically asymptotic result that we know in the sparse setting, and the following. So we forbid even cycles of whatever length, and we want to maximize 4 cycles. And this was obtained by Gerdner, Jerry, Mateusz, and Wieser quite recently, and we get the asymptotic value up to some lower order term. Yeah, so it's not a full solution, but gives a asymptotic solution. Okay, and if we concentrate on even cycles, so 3 and 5 is hard. One may think that maybe it's the same case as in the dense setting, and if we look for longer cycles, it will be easier. And it occurs that that's the case. So together with my master student, Mateusz Górski, we managed to prove that if a graph has at least 9 vertices, then this is the exact answer for the Turán problem. We forbid cycles of length 7 and want to maximize cycle of length 5. This n equal at least 9 is needed because if you take a smaller cycle, then the best is just to take a complete graph on 6 vertices, and this gives the maximum. Of course, it does not contain C7, and it contains quite many C5. And why this number? This is obtained in the following construction. So you take a triangle and a bunch of vertices which are isolated between each other and fully connected to the triangle. Yeah, and such a construction does not have a cycle of length 7 because any odd cycle needs to use at least one edge of the top triangle, and there are not enough vertices in that top part to close a 7 cycle, and it has many 5 cycles, exactly this number. And similarly as before, one can ask if this can be generalized, and we conjecture that this is the extremal construction always. So if you forbid any cycle of any odd cycle of length L, and you want to maximize odd cycle of length K, which is smaller than L and at least 5, then the best is to take like a top part, which is a clip of size L minus 1 over 2, and the bottom part, which is just isolated vertices completely connected to the top clip. And similarly as before, this graph does not contain a cycle of length L, and it has lots of cycles of odd lengths which are smaller than L. And we conjecture that this is asymptotically the best construction. Okay, and how one can prove it? So let me start with some ideas. There is a paper by Jerry, Salia, Tompkins, and Zamora on the Turán problem for paths. And there you can find exactly the same number. So this comes from the fact that if you take a vertex in the extremal construction here, then it's connected with all the other vertices. And moreover, any 5 cycle is passing through this vertex. And because of this, any path of length 4 in this construction can be prolonged to a cycle of length 5. Any path on 4 vertices can be prolonged to a cycle on 5 vertices. And any path of on 6 vertices can be prolonged to a 7 cycle. That's why this bound gives us exactly the same number as in the case that we are considering. The problem is that, of course, we don't know if there exists a vertex which is fully connected and appears on all 5 cycles. And the proof that they are using is the following. So if your graph has a vertex of a very small degree, like 2 or 3, then you can easily count what's the biggest number of paths that goes through this vertex. And then you can just remove this vertex and continue inductively. And if every vertex in your graph has quite big degree, then you will find a long path on 6 vertices. So this is nice for paths, but this is not working for cycles, because you can have a graph with big minimum degree. It's enough to contain, like, for example, big events, blow up of a big complete bipartite graph. Then you will have a big minimum degree, but you will not find any 7 cycle, right? So this approach is not good because we don't know what to do with vertices of big degree. But still, you can try to prove that through a vertex of a minimum degree, there are not many cycles of length 5. And if you prove that there are at most 6 and minus 24 cycles of length 5 passing through a particular vertex, then if you remove this vertex and use the induction, you will obtain exactly the bound that we want to obtain. Yeah, so one can ask if this approach, just find a vertex with, which is in a small number of 5 cycles, and then remove it and continue. So this is not good, and not only because of small graphs. As I said, if the graph has less than 9 vertices, then this construction is not good, but also for some bigger graphs, this is not true. For example, if you take a K6 and another K6, which is using one joint vertex, and now if you pick any vertex, it appears in a bigger number of 5 cycles than 6 and minus 24, right? So you need to do something more to get such a result. You need to go somehow get rid of some dense neighborhood of a particular vertex. One can try to use also some bounds using standard Turán problem for paths. Why such a bound can be useful? Let me draw it. So if I take a particular vertex and a particular 2 vertices in its neighborhood, and I want to count what's the number of 5 cycles passing through this cherry. The rest of the graph can be divided into 4 parts, either neighbors of just the top one, neighbors of both, neighbors of the bottom one, and the remaining vertices. And now you can see that if I take any edge like this, it gives me a 5 cycle, which is using those 3 chosen vertices, right? It appears in 1 5 cycle. The same if I choose an edge like this or edge like this, it appears in 1 5 cycle. But there are some edges like here, which appears in 2 5 cycles, because I can go in 2 ways with this edge. And also there are edges which does not appear in any of the 5 cycles using those 3 vertices. For example, edges like this, or edges inside the rest. But still, if I clean the graph by removing those unimportant edges, and then I can, an unimportant set, I can still have some paths of length 3, for example, paths like this, which are not in any 7 cycle using those 3 chosen vertices, but still this can be cleaned in a way to obtain the result that there are at most 2 times n-4 5 cycles using those 3 vertices. Yeah, so if I take a vertex which has degree at most 3, so this vertex has degree at most 3, then I can choose in 3 ways those 2 neighbors, which gives me that the vertex V will appear at most this number of 5 cycles, which is exactly the number here. Yeah, so in other words, if I have a vertex of a small degree, small means at most 3, then it's easy because I can just remove it and continue by induction. But the problem is what to do if I have vertices of a big degree. Yeah, so this approach fails if a vertex has degree bigger than 4. Sorry, it should be at least 4. Then this method cannot work and we need to do something else. So what we did exactly is to state what we did exactly, I need one more definition. I will say that the vertex is locally minimal if it has minimum degree among the vertices at distance at most 2, right? So not minimum degree in the whole graph, but I just look for its neighbors and neighbors of its neighbors. Yeah, and the theorem that we proved is the following. So if I take a graph which does not contain 7 cycles and the vertex which is locally minimal, then this vertex appears in one of the graphs below, in one of those 6 graphs, or in at most 6 and minus 24 copies of a 5 cycle containing P. Right? So this is exactly what we needed because it's also like containing those very dense neighborhoods that appear in the extremal construction for a small number of vertices, and contain the extremal construction for larger graphs when a vertex of minimal degree appears in at most 6 and minus 24, exactly copies of a 5 cycle. And this theorem can be proved inductively, and this is enough to obtain our main result. It's not straightforward that it implies the main result because you need to take care of vertex if a minimum degree appears in one of those 6 graphs. But this can be done in a way that we prove that it needs to appear in K6 and there cannot be anything else in the graph, basically. So this gives us this result that you're either K6 or you are at most those number of copies, which gives us the value that appeared in the external construction. Okay, I have a few minutes, so I will just make a short sketch of the proof. So since I'm doing the induction, the approach is quite straightforward. So I consider a minimal counterexample, and I consider a vertex of which is locally minimal. And if I manage to divide the graph into 2 parts, let's say this is like this is my vertex V, and I divide the neighborhoods and the neighbors there in a way that in the remaining part, in this vertexes without some specific set S.
Andrzej, do you mind going back to the previous slide? We have time, so don't worry. Just explain this a little bit more. It's a bit fast. So,
sorry.
What was the locally minimal?
So the vertex is locally minimal if it has minimum degree, but not in the whole graph, but just among its neighbors and neighbors of its neighbors. So just among the second, among the vertices at distance at most 2.
Mm-hmm.
Yeah, so why it's important for me to do it locally minimal, because I would like to cut out some pieces of my graph. So this set S, let's say, this is the part that I want to cut out. And I will lose track of the degree of vertices which are far away. I don't know if they have, maybe it happens that they have lots of neighbors in this set that I cut out, and they will suddenly become vertices of the minimum degree. But if I concentrate only on this local minimality, I just need to take care that the vertices which are at the neighborhood of V and the second neighborhood of V are not, their degree will not drop down too much. So in other words, if I manage to find such a set S, like here, such that there are no, let's say, edges like this. Oh, sorry, it's not a good picture. There are no edges like this or like this. Then after cutting out this set S, vertex V will be still a vertex of which is locally minimal in the remaining, in the V minus S, because I reduce the neighborhood of V, like the degree of V, by just this set, and I remove reduce the degree of other vertices here and here only by just this set. So if I manage to do it, and at the same time I manage to do that there are not many copies of a 5 cycle passing through S, and at most 6 times its size, then I obtain a smaller counterexample, so I could use induction and continue. Yeah, so my main idea is somehow construct a set S that I can cut out without losing too many copies of C5 containing V, and without losing the assumption that V is a locally minimal vertex. And if I manage to do it, then in the remaining graph I can use the induction hypothesis, or just use the fact that the graph was the minimal counterexample, so it's not possible that the rest will contain at most, in this case, would be 6 times size of V minus S minus 24, right? Because I remove 6 times S.
What was your theorem on the previous slide?
Yeah, so the theorem was that if I take a locally minimal vertex, then either it appears in one of those structures, or it is in at most 6 and minus 24 copies of C5.
And why is this enough to prove the bound for C5, C7 for the generalized Turán number?
So to prove the main theorem, like to prove this bound, I just pick up a vertex of a minimum degree. And if it's not in one of those structures, then from the theorem, it's in at most this number of copies of C5. I can remove it and I obtain a graph which is smaller. And this number is exactly what I need to have between n and n minus 1. Yes, so I can reduce the graph smaller and smaller. And if it appears in one of those structures, then it needs like a 1-page proof or 1.5-page proof that either it appears in K6 and there is basically nothing more, right? Basically 3 more vertices, and this is giving me this first part. I mean, in this part, that this vertex appears in this number in K6, or let me move back. If it's not in one of those structures, then it's at most 6 and minus 24 copies of C5. So I can still reduce it and get a smaller example. So
when you say V appears in one of the graphs below, it means your graph is basically one of this small...
No, I mean, for example, V can be in a K6, so this is K6, and the graph can be like longer, there can be lots of other stuff, right? But so intuitively, if it appears in K6, you can see that there cannot be, I don't know, vertices which have degrees, which are neighbors in a K6, because you can close a C7, right? So if V appears in a K6, it highly reduces how the neighborhood to this K6 goes, and since V is a locally minimal vertex and has something like except the K6, it means that those vertices in K6 need to have lots of neighbors, which are not used at all in 5 cycles using V, right? So if you have K6 and something more, then still this vertex V appears in at most this number of copies of a 5 cycle. So the best is to have just K6 and nothing more, and this gives this first part of our theorem that for small n, it's best to be just K6. Is it answering your question?
Yeah, what for K5 then you analyze, I guess, more.
Yes, so if it's one of those others, it's easier to see that the bound will be worst. And still you have similar properties. For example, like any vertex cannot be connected to 2 vertices here because you can close a 7 cycle.
Mm-hmm.
So it's dense enough to give me all I need. And it's sparser than K6, so it has less 5 cycles than I need.
Mm-hmm. Thank you.
Yeah, so how we do it, well, you can think that some specific structures in G, in this minimal contour example, are bad for me. For example, if I have a vertex, this vertex V, and I have a vertex in the second neighborhood, which has a big neighborhood, the joint neighborhood with V, and also it has many neighbors in the second neighborhood. Right? If I have such a vertex, it appears in many 5 cycles using V, because I can go to X in many ways, in 2 steps, and then I have many neighbors of X, so I can like continue and I can obtain lots of 5 cycles. But at the same time, if I have such a construction, then I can cut out the rest, or maybe I'll draw the picture. Unless we don't have time.
No, it's okay. Take your time.
So if I take a vertex, and as I drew before, let's say it has big neighborhood, joint neighborhood with my vertex V, and it has some neighbors in the second neighborhood. Then if I consider like neighbors of this joint neighborhood, and I want to cut out this part as my S, then notice that if I have like other neighbors of V and the second neighborhood and continue, then I cannot have specific edges. Like I cannot have an edge like this because it's easy to complete 7 cycle using this edge. I just go from V, right, like this, and then use X to close a 7 cycle. Yeah. That's why I cannot have those red edges here. And I also cannot have red edges like this because I will close a 7 cycle using those neighbors of X inside second neighborhood. And since I don't have such neighbors, I can easily cut out this S, and I will guarantee that the vertex V will be still locally minimal in the remaining part. And moreover, because there are no such edges, there are not many, there are no cycles, 5 cycles using both S and the part outside S. So they need to be contained inside S. And also there cannot be too many of them because still, like if I try to use a 5 cycle, which is going like this, then still it can be prolonged to a 7 cycle using X. Yeah, so still there cannot be too many 5 cycle inside S, and I can count it properly and get this bound 6 times size of S, which gives me a smaller counterexample than the contradiction. Yeah, so this way I can get rid of this hard part where X has big neighborhood, joint neighborhood with V and some neighbors inside second neighborhood, and I can continue. So now I forbid my vertex in the second neighborhood to contain at least one neighbor. And now the counting is a bit different because this one neighbor can have neighbors outside S. So we need to count them, but it's just one vertex, so it's easier to count and bound. And you can imagine that the next step would be to consider vertices without any neighbors. So now there can be neighbors of some neighbors to from S to outside S, but some bound we get a smaller number of 5 cycles using second neighborhood because vertices there does not have neighbors in the second neighborhood. And I can continue then just use similar approach to prove that there cannot be a vertex in the second neighborhood which has joint neighborhood with V at least 2. And if I exclude such structures, I get a graph which is really nice because I know that any edge in a second neighborhood appears in exactly 1 5 cycle, right? Because I can go to this vertex only in one way. It cannot have 2 joint neighbors with neighbor plus V, and also from the vertex here. So I can use this fact. Okay, I can prove that there are not many edges in the second neighborhood, and all the other 5 cycles that use vertex V needs to be completely in the neighborhood of V, which is exactly the bound I used here. Yeah, the bound here. Yeah, if I have a vertex which is completely connected to some part of the graph, right? Then all the 5 cycles which are up here I can bound using this. So Jerry and others bound on paths. Yeah, so if I combine those, I get a bound that we wanted to prove. So this is a very rough sketch. In order to make all the details work, it needs some proof. But you can imagine that this is just counting and excluding some structures which are on one hand nicer in terms of constructing this set as which won't be connected with the remaining, but at the same time there are more 5 cycles using S. So if I divide into those steps, I get just that either vertex is nice from one hand or nice from the other hand, and appears in a small number of 5 cycles. Yes, so this way we can prove it. And the bad thing is that it's quite technical and long, so it's not easy to generalize, but still I hope that some parts can be generalized by some different constructions or more general reasoning. So let me finish with reminding the 2 conjectures that I mentioned. The first one was for the dense case. So if you want to maximize number of cycles, like longer odd cycles, if you forbid shorter odd cycles, then the best is to consider balanced blow-up of size L+2, like a bit bigger than the forbidden cycle. And in the second case, in the sparse setting, if we want to maximize number of small odd cycles and we forbid big odd cycles, then the best is to have a clique of size L-1/2 and an independent set of the remaining vertices and all possible edges between. This is the conjecture that we are stating. So I hope one of you will be able to prove it, or at least help us in giving some insights and ideas. Thank you very much. I hope you enjoyed the talk.
Thank you, Andrzej. I invite everyone to unmute themselves and give some applause to Andrzej.
Thank you.
Thanks for having Armenian on the...
Yeah, it's not easy to write Armenian in LaTeX, but I managed. I hope it's correct.
Did you ask Hrant how to?
No, I just asked Google.
Okay, good.
So that's why I hope it's correct.
It is actually. very correct. Right. Any questions?
Andrzej, can you show the two questions again? I just want
Yeah.
to adjust. Okay, thank you.
And the slides are already online on the seminar webpage. So if anybody is interested in the conjectures or some results I mentioned earlier, you can just look at the slides on the webpage.
But basically, there's no part where you use log algebras, right?
No, there are no flag algebras in those reasoning at all.
Yeah.
Yeah, like in the sparse setting, flag algebras are useless, right? Because it will give you that density is 0 and nothing else.
Yeah.
Andrzej, can you say a few words about what's known on the sparse case? I know you mentioned several results earlier.
What do you mean for cycles or in general?
No, the sparse case, the second conjecture.
Yes, so I think only our result is the only one that it's exact. I mean, it was for 7 and 5. And except this, we have only Gish-Boliner and Shapila results, which provides us the order of magnitude, right? So we only know the order of magnitude except the result that I just mentioned. Yeah, so the next step would be maximizing 9 cycles in 5 cycle free, maximizing 7 cycles in 9 cycle free case, or maximizing 5 cycles. Yeah, 5 cycles in 9 cycle free would be the way to go, I think.
Okay, thanks.
You're welcome.
Andrzej, hello, thank you for the talk. Do you know if this sometimes called the split graph example for this sparse case here, does that have the correct number of triangles to maximize triangles without 7 cycles?
Yes, like this is the concept. If you talk about, if I understand correctly, you are asking about maximizing triangles in C7 free, right?
Yes.
Yeah, so I think this is not the best you can do, because the better constructions are obtained in the following way. So you take a graph which does not have, let's say, it's a bipartite graph which does not have C6. And then what you do, you take a vertex in one part, and like all the vertices in one part, and you blow it up to edges. So one part I changed into the following way, that every vertex becomes an edge. And this way, any C6 between would become a C7. And so if I start with a graph without C6, I will obtain a graph without C7. And every edge between becomes a triangle, right?
Sure.
Yeah, so this gives a big number of triangles and will not contain C7. And I think this is the best construction that we have. So just consider whatever you can have a construction for standard Turán problem for C6, and just do this trick of blowing up a vertex to an edge.
Okay, so once again, it seems triangles are the weird ones.
Yeah, triangles are different, definitely.
So that's really something I asked earlier. For the triangle case, it's kind of equivalent to the Turán number for three uniform cycles. So those Yeah, very different. If you replace, for instance, if you replace your L, say replace CL with KL, then I think that will also reduce to the bridge to run problem. So whenever you're forbidden, whenever you're counting clicks, I think it's related to the bridge to run problem.
Yeah.
So C3 is special. I think it's because it's K3, happens to be the split key.
Exactly.
Thank you.
You're welcome.
Thanks, Andrzej, once again for a wonderful talk. It was
Thank you.
really, nice